So entropy is something that is slightly strange, because if I look at the canonical ensemble, what is the expression for entropy? It's S is Kb d by dt t log of z. And thus we see that it'll contain a term which has just log of z in it. Therefore, it'll depend on h bar. Okay. But in classical mechanics,
Sir, could you explain why? Because when we write the partition function, why would h appear on that in the case of ideal gas?
Oh yeah. So h, we define the partition function as 1 over 2 pi h bar cubed because of dimensional reasons, right? I don't know if you were here earlier today.
Oh yes, I just missed it.
Yes. So
Sir explained it.
yeah. So anyway, it's not. Yeah. Don't worry about it. So that's why So when we do the differentiation, there are going to be two terms, and one term is going to have log of z, right? But in classical thermodynamics, we never compute the partition function. What we compute are differences of. Sorry, we never compute the entropy. What we compute are differences of entropy, and therefore, there is really no contradiction. Now, here we are going to, let's define a different version of the partition function. Let's call it z bar of n, which is v to the power n, lambda 3n, and use the fact that all our particles are indistinguishable. Then we divide by factorial of 1 over n. Well, divide by 1 n factorial. And this is, again, something that drops out for most classical calculation, because of the same reason as before. Because when you take the derivative, these things drop out from the log, but not in entropy. Okay. So if I compute the entropy using this expression, then just a short calculation, which let me just do because it's worth doing. So entropy is Kb d by dt. There is t and then log of Zn. And this is going to be one term, Kb d by log of Zn. So the term where it acts on this. And then we're going to have another term, which you can work out very easily, is going to be 3n Kb over 2. And then we use the Stirling formula and expand this, and you will get two terms here, and one of the terms will add up with this term and give you Kbn times 5 by 2. The other term will give you log of V divided by log of Vn by lambda cubed. Okay? And here we see it has got a lambda dependence. Now, if I didn't take this n factorial into consideration, I would get a different result. I would get 3/2 here, and here I would get log of V by lambda cubed times Kbn. So I would get a different result for the entropy. So this formula is called Sackur tetrode equation. And this equation explains a paradox which is known as Gibbs paradox. And let me, in the last 5 minutes, explain what the Gibbs paradox is. So if I take, a gas, and consider its Joule expansion. So the gas expands, it's got N molecules. Then the change in entropy, the classic is going to be Kb N log of 2, right? Because the volume is increasing by a factor of 2. But now if I have 2 N gas molecules, then, thermodynamics tells us that delta of S is 0. But, we can think of it as this amount of gas being able to expand in this here, and this amount of gas being able to expand to the full. And if I were to take 2 different kinds of gases, here I have one type of gas, and here I have another type of gas, and I let them mix, then, we know that the change in entropy in that case be Kbn log of 2. So 2 times Kbn, because we've got, so, from one point of view, why should this be 0 and this should be non-zero? And if I were to use this formula, then they would actually be the same. These 2 cases would be the same. But if I use the Sackur-Tetrode equation, then we can show that this is different from this, because in this case, this is truly indistinguishable, whereas here, it is distinguishable. So Gibbs' paradox, and Gibbs proposed on the basis of this paradox that fundamental particles should actually be considered as indistinguishable, okay? Same kind in this situation. So even before the discovery of quantum mechanics, Gibbs had the intuition based on this paradox that, particles should be indistinguishable, okay? So, statistical mechanics and taking the indistinguishability of the particles explains the Gibbs paradox. Okay, so I think I'm going to stop here. So any questions?
I have a question about an earlier part of the lecture.
Yeah.
When you were writing the Hamiltonian and stuff, there was a bar above the P. Was that average or was that vector?
No, it's vector. It's three-dimensional vector.
Okay.
Yeah, I think that I meant it's yeah. I should have used this.
You viewed this 2-gas system with 2 equations. Could you explain those 2 equations significance again?
Yeah. So here we have the case where we have 2 same kind of gases in 2 different chambers, and we have a partition in between. And when we remove the partition, this bit of gas expands into this bit of gas. This bit of gas expands into this bit of gas. So, and here we have 2 different kinds of gases, with the partition. And when we remove the partition, this gas expands into this gas expands into this gas. So from this point of view, the change of entropy of both these cases should be delta S to Kb n log of 2. But we saw that another way of looking at the first system is that, this is the same gas with the partition in between. And therefore, when we remove the partition, nothing changes. No heat comes in, no work is done, the volume doesn't change, and therefore, the change in the entropy there is 0. And that is that thermodynamics result. But if we could follow all these particles around, then of course the entropy should increase, because we could say, oh, the particles here have more places to go to. But this only, and therefore, it's the change in entropy should be this, not 0. But if the particles are such that truly they're indistinguishable, that when you remove the partition, there is no way of telling which particle went where, then we can say that, okay, then we have indistinguishable particles and the entropy change should be 0. Okay?
Yes, sir. But I am still confused where we get 3/2 and we get 5/2 in another equation. Just a bit.
Oh yeah, that's a okay. That's a yeah. Okay, I see. You know, basically you have to do the calculation here. Is that here you get 3 halves, right? And then when you look at this guy, you know, what you will get is that you will in log of Zn. So let me just like write out this term over here. So we have Kb log of Z bar n, and here this is going to be Kb, and if you look at the log, there's going to be you know, here we have a factorial of n in the you know, and that fact in where do we have that? We have a factorial of n in the denominator, right? So we can write this as n log of v by lambda cubed minus log factorial n, right? Because z bar of n is v to the power n divided by lambda 3n by n factorial, right? So we can write this like that. And then what we can say is that like kb, and then we have n log of v by lambda cubed, and this thing can be written as minus, using Stirling's formula, minus n log of n plus n, and then minus 1, but we can ignore the minus 1 because it's multiplied by kb, which is a small number, right? And then if I factor out you know, n, we get kb of n, and then we have log of v by n lambda cubed, and then we have and then we, you know, this n we can absorb it, or we have absorbed it here, but this guy is just 1 plus 1, and then there was 3 halves. So when we add these two things, we get 5 halves. Okay.
Yes, sir.
Okay. Any more questions?